We are up and running. So she noticed the projector seems to be playing up in here a bit, and we had to get the old stick system in. Well done, thank you, to get that functioning, but we are up and running. Some of you will know me. My name is Mike Calver. For those who don't know me, I'm an animal ecologist within environmental and conservation sciences here at Murdoch. And Peter has asked me to come and have a chat to you a few times during this unit about particular topics within my area of expertise. And what he's asked me to do today is to give you a quick overview of the role of populations in conservation biology, and in particular to revise some of the key concepts regarding populations that you guys will need to know and understand to make sense of some of the conservation applications later in the semester. So what we're going to be doing in the lecture today, bear with me while I set the pointer, is first of all looking at why we need to know something about population biology in relation to conservation, then some key concepts. How do you measure a population? How do you calculate population growth? What happens with metapopulations? Then to look at what happens in small populations, and in particular minimum viable populations and the so-called outing effect. And finally, we look at the effect of chance. You'll come across this word occasionally in relation to models, this stochasticity. It simply means chance variability in a system. So that's where we're going in the lecture today. The slides themselves are online, I believe, in the unit LMS. For those of you who are looking up there, I wanted to use them to follow as we go through this morning. So why do we need to know something about population biology to actually be able to apply it in conservation? Well, essentially, it's the populations that we manage or we harvest. So you see the dog perched on top of all of the skins there. These have been harvested around about the turn of the 20th century in Australia. There's a very ancient vehicle there. So we need to know something about populations and how they behave if we are to harvest in a sustainable manner. I mean, it's very, very easy to keep taking things until they're all wiped out. But if we want to ensure that the population itself is robust and will continue to produce individuals for harvesting, then clearly we need to know something about population biology. We also need to be able to sort out, one, why a population is declining, or two, what kind of processes are happening in small populations as a result of decline. Now, this is an idea that we will return to repeatedly during the unit. It's an idea that came up from a gentleman by the name of Graham Corley, one of Australia's most distinguished conservation and wildlife biologists. And Corley argued that there were two paradigms in conservation. One was what he called the small conservation paradigm. And he argued that we knew a good deal about this. And the small conservation paradigm is what goes on when a population is small. I'll talk a bit about that this morning. You'll be hearing from Kate Bryant later in the unit about what's going on at genetic levels within small populations. The point being, one paradigm, the small population paradigm, and we know a darn lot about it. The second, and Corley said this one, is perhaps in some ways even more important, but we know less about it. And this was what he called the declining population paradigm. And that was, why has the population become small? And he said in that context, we know comparatively little, yet it's incredibly important to be able to answer that question if we are to do something about the decline, to arrest it or reverse it. So population biology is certainly important in understanding what happens in a small population. That's the small population paradigm, but also the declining population paradigm. Why is the population shrinking? Why is it becoming small? And then, of course, knowing something about the small populations, we can seek to improve their viability, their chances of persistence in the face of threats. And we can manage them, hopefully, to the point of recovery. So that's why we need to know about the population biology. We also need to get some key definitions straight in our minds. And one of the issues you'll find as you work through conservation biology is that many of the terms that we actually use are terms that have an everyday English meaning, definition, understanding, but a much more precise and targeted one within conservation biology. So going over the definitions is actually quite important so we grasp and understand properly what we mean by the definition in conservation. And so for population, we can define it as organisms, the same species, in a particular place and a particular time. Now, in this particular situation, we are focusing on species, a place in time, and a spot in the physical world. And that is telling us what population is. So, for example, the human population of Australia, the population of lichens in Tasmania, we can define the population in terms of species, physical location, and location in time. The second definition here that we can apply to a population puts it in an evolutionary perspective, and it considers the population as individuals of the same species that have a selective environment resembling that of its neighbours. So now we're looking at not just how many are there at a particular place and a particular time, but we're considering what that context means. What is the environment that they interact with, physical and biotic, and how can that influence the population? So we can look at populations in both of those ways. So what things then can we turn to measure if we're wanting to talk about population? Well, one of the most obvious things that we can turn to is how big is the population? And the statistics that we can use to measure that can vary quite considerably. It's not just a head count, which indeed we may do, how many individuals actually are there, but we can turn to other things. We can measure the biomass. So if we work together about how many individuals there are and how much each of those individuals weigh, well then, what's the overall biomass of the population? We can also look at density, which is individuals per area. And so we now begin to get an idea of whether these individuals are tightly clumped together, whether they are thinly spread across the landscape. We can get the measurements from density. And in relation particularly to plants, we can calculate cover. And cover is usually defined as the ground area that is occluded or obscured by the vegetation. So these are some of the things that we can measure to get at size. We can then turn our attention towards dispersion. And in dispersion, we are concerned with how are they distributed across the landscape. Are organisms of a species, for example, or a population, distributed randomly without any relationship to features of the landscape or to each other? Do they exist in clumps? In other words, do they form social groups? If you find one, you're likely to find others nearby. Or are they what we would call over-dispersed, which means they're not random across the landscape, but they're actively avoiding each other and keeping to a distance. So we can look at dispersion as a factor here. And we can measure processes that go on inside a population. So we can look at birth rates, for example, longevity of individuals, death rates, fecundity, number of individuals per female, these kinds of questions. So these are all examples of things that we can measure in populations. And I've listed some others for you here. So all the factors that are associated with bringing in new individuals by natural increase, so that's mortality. Then you can have individuals moving around in space, that's migration. And all of these things can be integrated into the concept of the MVP. And the MVP is the minimum viable population. And that is the smallest size the population can be and still be capable of reproducing itself and sustaining itself in that environment. So these are the key concepts that we seek to measure about populations. And we can diagram them for you in a fairly simple manner like this, thinking of it as a large tub with water in it, where the tub itself is, or the water in the tub indicates the population size and the various factors that can increase birth, immigration, and the factors that can decrease death and immigration. And so basically, we often use the capital letter N to indicate our population size. And birth obviously contributes to the water in our tank. So you can tap there, some drips going in. So those are the birth rates, commonly indicated as capital B. And then we've got deaths. So it's putting the tap there below the water level and it's taking water out, commonly abbreviated with a D. Immigration is also adding, that's an I. And then we've got immigration, again taking individuals out, and immigration gets an E. So we can produce a very, very simple equation to say the change in population size, that's what this delta symbol means up here. So change in population size equals the births plus the immigrants minus the deaths minus the immigrants. Not particularly profound, it's one way in which we can represent this information. But we can do something a lot more sophisticated than that. And my example for this comes from the red fox, an introduced predator into Australia, where it has been responsible for population declines and even extinction of a range of native Australian animals. This particular red fox is feeding on the carcass of a kangaroo in semi-arid areas in Western Australia, and indeed throughout the southwest of Western Australia, these animals are targeted in culls, known as red card for the red fox, systematically shot across the landscape in an attempt to reduce their impacts both on native biodiversity and also the problems that they cause for agriculture. So we've got here a quite large number of animals that have been shot as part of this, and from data such as this, one can go and calculate life tables. And the life table basically is a summary, a snapshot of what's going on in a population. Age structures, breeding, various other things. There are two ways to calculate a life table. One is known as a cohort life table. And in this, I'll take humans as an example, you might take all of the people born in 1970 in Australia and follow each one of those individuals through the entire life history, noting when that individual has children, noting when that individual dies, all of this sort of information. And that's called a cohort life table. So you take a group entering the population at a given time and follow that group all the way through and see what happens to them. Or you can do as is done with the red fox in this particular example. You can take a life table that is a static one. It's a snapshot of the whole structure at a single point in time. This going to go out and shoot them, and you get animals at different ages, and that's the snapshot of the population at the given time. Let's unpack what's going on inside this life table and the various things that it's telling us. First of all, you age your foxes. So there's the age over here in the left-hand column, and it's in years. I'm not sure why it's been decided not to round them to single years, but at any rate, so you've got those animals that are entering your population here, those that are aged up to 0.75 of a year, 0.75 to 1.5 years, and so on to the most long-lived individuals which have been hanging in there for over 3 years. We can also look at the number, if you like, that enter, so the ones that come in here. So all up, we're talking about 94 entering. And then you can basically see them distributed across the different age categories. So all of them enter. If you then express it as a proportion, so these are these numbers now. So if you put 51 over 94, you'll get 0.543 and so on. So you're looking at the proportion of the cohort that enters each age class. So we can see that only 0.064 of the cohort will actually live to be over 3 years of age. We can also then, by simple subtraction, work out the number that die in each particular interval. So these are the deaths, grouped down through here. We can then obviously calculate the probability of dying in a particular age interval. You can see those figures down through here. And then, if you happen to be female, we can know how many young you produce. So from an age of about 0.75 years, females begin to breed, putting out approximately 2 youngsters a year. Now, the reason why we focus on females at this point is that in red fox populations, and indeed is true in many other mammals, it is the females that are the determinant of the reproductive capacity of the population. One male, assuming he's fit and healthy, can get around and service a large number of females. You don't need an equal sex ratio, but if you've got, say, a population of 2,000 males and 10 females, you've got a severe reproductive bottleneck. If you've got it the other way around, he may die of exhaustion, but you're still going to produce a large number of youngsters. So often in the life tables, we model on the female, and that's why it's in there. And then finally, this statistic across here, this is the number of female young produced that has been corrected for survivorship. So she's got to survive into that age class, and then she's got the opportunity to produce young. And we calculate this figure by multiplying the LX, that's this column here, by the MX, which is the number of female young produced. And we can deduce quite a large number of things from a life table, but probably for our purposes, one of the most interesting ones down here is the rate of increase, the R0, which is produced simply by summing the LX, MX figures. In this case, it is 1.49. If you have a number of 1, the population is exactly replacing itself. If you have a number greater than 1, the population is growing. And if you have a number less than 1, the population is in decline. So you can see how we can use this detailed information to start making comments about trends in population size. So life tables, you can produce them by following a single cohort through, or you can take a slice through the population in time and take a look at it, and from this we can calculate the useful number of statistics about our population. Now, those survivorships, how many make it to the next stage of our life table, can also be used to give rise to a so-called survivorship curve. And these are characteristics of different types of animals with very characteristic biologies. If we look at this graph here, we have along the horizontal axis the percentage of the maximum lifespan. So 100, it's not years, it's when the last individual dies. And on the vertical axis, we have the logarithm of the percentage of survivors moving on to the next age class. And if we actually look at different kinds of organisms, many of them fall out on one of these major types of survivorship curve, imaginatively called 1, 2, and 3. Survivorship curve 1, if you look at it, is characterised by very high survivorship of the juveniles. So as we can see, death rates really don't start to kick in until well into the lifespan. There's a gradual slow decline during those earlier years, but on the whole, most individuals aren't starting to shuffle off the mortal coil until they're quite old. The type 1 survivorship curve is usually also associated with producing few young and investing a large scale of corrective. So that's why we have the elephant chosen here as an example. Juvenile mortality rates are quite low, few young are pumped out, and the parents put massive efforts of care into them. The other extreme is the type 3 survivorship curve. And in a type 3 survivorship curve, mortality is very, very high in the young stages and tends to level out at the older ages. So examples here, many of the arthropods, we've got a grasshopper here by way of example, show a type 3 survivorship curve. They pump out loads of youngsters, huge numbers of eggs, and very few of these will survive to adulthood. And the parents invest very little or no care in their offspring. So those are the two extremes, and then two, sitting in the middle, illustrated by little synopsis there. What we have here is a situation in which mortality rates are very even across the life history, and the level of paternal care invested in the offspring variable, but certainly not as much as you get in type 1, and certainly more than you get in type 3. So again, from our life tables, we can begin to get an idea of what kind of survivorship curve is shown by particular species. And it doesn't take much imagination to turn this into practical application. And as you seek to turn it into practical application, obviously, if you have an organism with a type 1 survivorship curve, and you get in there and you start taking out some of the youngsters, they're going to be in real trouble. They don't have the capacity to replace them easily, and you can cause a lot of problems to the population. On the other hand, if you come down to something with a type 3 survivorship curve, you've now got something that is probably very amenable to harvesting. So in other words, because they pump out lots of youngsters and don't invest a lot of care in them, if you're careful about how you harvest them, you can take quite a decent number out of the population without damaging their stability on an annual basis. So you can see how that works. You can also see how it might function in terms of pest control and why it can be so darn difficult to bring organisms with type 3 survivorship curves under control, because they're pumping out these huge numbers of offspring at very little cost, and they make good their losses very quickly. Now, should you want to go back and revise life tables a bit more, many of you will recall them from your studies in the ecology unit, but if you feel like you want to go back, and remember these slides are up online, so you don't need to copy down web addresses. I have checked the address, yes, it's still up there and valid. You can go to this slide, and they have some wonderful spreadsheet exercises in which you can quite simply generate some data, calculate some life tables, explore the implications of different numbers in the life tables. So if you feel like you'd like to revise and have a go, this is a really good site. Okay, so we've talked about how to measure our populations. We've taken ourselves all the way through to life tables, how life tables can be used, and we've looked at deducing from them survivorship curves and the implications of our understanding of biology and population management from those survivorship curves. We now need to turn our attention to growth and also to relation to growth declines. So why on earth would I show a chess set at the beginning of this? And it's because there's an old Indian legend that says that chess was invented by the games master of an Indian king. And the king himself was so enthralled and fascinated with the new game, so terribly excited, enjoyed it so much, that he said to the games master, "Whatever you want, just name your price. This is such a wonderful game. Name your price and I'll pay." And the games master said, "Well, all I'd like is some wheat. 1 grain of wheat for the first square on the chessboard, 2 for the second, 4 for the third, 8 for the fourth, and so on." "Really?" said the king. "Is that all that you're asking for? A few grains of wheat for such a wonderful game?" And so he immediately said for the royal mathematician to calculate how much wheat it would be. Now, for those of you who understand how exponentials work, this is effectively 2 to the 64th power. And you can attempt to calculate it if you wish, but it's probably more grains of wheat than even exist in the world today. So it's a huge, staggering sum, from very small beginnings to a huge number. So how does our legend finish? There are actually 2 divergent views on this, In one, the king goes broke trying to pay his debt, and in the end, the games master replaces him and becomes king. In the second version, which I think is probably more likely, it simply ends with the ominous sentence, the royal games master had invented his last game. So, growth. What the example of the chessboard indicates is what is known as exponential growth. And this is a situation in which a population increases at a constant rate, but because increasing at a constant rate at small population sizes, it seems to grow very slowly. But as the population gets bigger and bigger, so that constant rate of growth enormously increases the number of individuals we see. That's exponential growth, and it's illustrated in the top graph here. But we all know from our own experience that growth of this sort does not happen indefinitely. At some point, the brakes set in. And so we can modify the equation for exponential growth by building in factors that break the population as it hits towards higher levels. If we do that, we produce the so-called logistic growth curve, which is shown at the bottom right here. And in the logistic growth curve, we actually begin with the population growing in exponential fashion. Slowly at first, then as we get more individuals, that constant rate of increase really means a lot more individuals each year, and the population really starts shooting up. But then the various breaks on population growth come in. Is there enough food? Is there enough space and shelter? All of these things can begin to break the population. Sometimes as the population gets bigger, it attracts the attention of various predators. Oh, good friend here coming in. So all of these factors can act to put a brake on the population. And the horizontal line here indicates the point K from the equation below. Those of you who are frightened a little bit about mathematics, don't try and understand the equation, just grasp the concept verbally. But K is commonly called the carrying capacity, and it represents the largest number of individuals of that population that the environment can sustain. And so what we see in the logistic growth curve is initially exponential growth, then other factors come into play, they break the rate of growth, and you can see the population stabilised at K, the carrying capacity. Now, in real terms, what often happens is that populations will overshoot the carrying capacity. So they get up to a very high level over that carrying capacity, and then the constraints really kick in and the population crashes to a level below carrying capacity. But the general concepts here, mathematically, we can describe exponential growth, we can describe logistic growth, and logistic growth gives us this very useful concept of the carrying capacity. It also indicates to us that if we want to harvest the population, we're wanting to harvest the population to try and keep it at or close to carrying capacity. The various factors that can act to put the brakes on population growth can be defined as being abiotic or biotic. And abiotic factors are those that come from the physical environment. So climate and weather, for example, are abiotic factors that can influence a population size. You get a severe drought, free water's not available, individuals are going to die. So that's one example. Conversely, at the other extreme, you can have floods or freezing conditions, and you can get deaths resulting. There can be various abiotic resources that are required by a population. Think, for example, shelters, as in that might be provided by rock outcrops or some other physical feature of the environment. These are examples of abiotic resources that can influence the population size. And then, of course, populations can be influenced by a range of biotic factors. Predators, for example, will obviously be killing individuals in the population, taking them out. They may also be outcompeted, driven away from resources by other species. Think, for example, the introduced honeybee in Australia likes to nest in hollows of trees and cavities under rocks and things like that, which also happen to be places where various other species like to rest. The honeybees are in competition for them, and in some cases will drive them out. Then you have pathogens. These are the disease-causing organisms, you know, fungi, bacteria, viruses, or whatever, and they, of course, will spread more effectively if you have a situation where the population is quite dense and they have very, very easy means of getting from individual to individual. And, of course, conspecifics can also be threats. So in some cases, as population densities rise, animals will fight amongst each other, plants will shade out other individuals of their species or compete with them for water or food resources. So we have our abiotic and our biotic factors that can influence the population size. I almost forgot, but before we leave this, we can also talk about these factors as acting in a density dependent or a density independent way. If they act in a density dependent way, the factor will act depending on the size of the population. That's density dependence. So population size influences how severe this is, that's density dependent. If it happens regardless of the size of the population, that is density independent. So if you have a situation, for example, the drought, basically no water, you die out, it doesn't matter how big the population is, the water's gone, they're all going to go. It will function in a density independent way. But something such as a disease spread, a pathogen, may function in a density dependent way. It may become a problem at higher population levels and not really be a problem at lower levels because diseased individuals die quickly before they can infect somebody else. So the abiotic and biotic factors can act in density dependent or density independent ways. We now move to a consideration of the metapopulation. And the metapopulation argues that populations do not have to be continuous. They can be divided into a series of subpopulations connected to each other by migration. So the migration move, or migrants move between the subpopulations and so exchange genetic material and so on. And subpopulations may form, die out, and so on repeatedly within the overall structure of the network called a metapopulation. We certainly find these are characteristic of island archipelagos. We also find them where there are discontinuous habitat patches and where natural influences or human activities such as agriculture and urbanisation have broken up and fragmented what were once continuous populations. So that's the metapopulation, a group of subpopulations connected by migration. And obviously the migration rates that you encounter are determined by a range of factors, including how harsh the intervening habitat might be, the distance that animals have to travel, do you have an excess of individuals who are available to disperse, and the dispersal capabilities of the individuals. Birds, for example, flying insects, they can cover large distances very easily, a little bit more problematic for a snail, and for plants, they rely on animals, wind, water, and so on to disperse their propagules, and again, they will vary in their dispersal capabilities. So we can diagram all of this as suggesting that there are patches of suitable habitat for a species, indicated by these stars, within a sea of hostile habitat. If you think islands in an archipelago, that's pretty obvious, but it can also function for suitable habitat within a fragmented environment. And over time, certain areas may become less suitable for the species. Either they're exploiting all the resources, or predators have found the subpopulation, whatever it may be, but the patches don't always stay as desirable. But new patches can appear, brought on, for example, by vegetation, colonisation, and so on. So we then have migrants leaving the old patches and seeking to find new ones. If they find a new one successfully, that's great, they'll breed up in there and away it goes. Sometimes the migrants will die. So we've got the migrants constantly on the move, recolonising. If you have patches close to each other and the dispersal is good, things will tend to work quite well and the full use will be made of the resources available. But the greater the distance between patches, the greater the risks associated with migration, then not all of the patches will be found and exploited. Some of the resources will go unused. Clearly the concepts of metapopulations are important for us in managing many species, especially in areas where humans, through agriculture, urbanisation or other land use, have greatly fragmented habitat. If you'd like to practice some of these metapopulation dynamics, again I've given you a couple of websites here. Yes, the links do work, I have checked them out, and you can go and explore some of these ideas further if you're curious in that direction. But we now want to turn to the final set of our examples, and this is to do with chance effects. So this term stochasticity refers to random chance and its influences. And with regard to populations, these can happen in terms of characteristics of the population itself, so that's demographic, the environment, physical and biotic, in which the organisms are placed, the genetic composition of the population, and we can also have events that are so extreme, outside of the norm, so left field, that we call them catastrophes. So all of these are chance effects that can influence a population. So what's going over here on the right-hand side with this diagram? This is meant to indicate the influence of random factors or chance. So it's from an old European legend, but basically the bloke is a drunk and his unfortunate horse just happens to be his unfortunate horse. And so you can imagine what has happened for year after year. As a pub at closing time, honey. Oh, yeah, where are you, Eddie? Eddie! Eddie! Oh, excuse me a moment. Eddie! Eddie! Why, Eddie? Oh, you're tall tonight. No, come back. Okay, Eddie, we'll walk. Oh, that was storm. Oh, where's the cliff, Eddie? Where's the path, Eddie? I can't see. It's too dark. It's... So, catastrophes. There's no recovery from them. They're extreme. And they're unpredictable in the sense that they don't happen with sufficient frequency that you can actually start to try and model them, but they can happen. And a real biological example of this concerns this little guy, this little rock wren, and it lived on this island, San Benedicto, which is here in the Pacific Ocean off the coast of Mexico. And San Benedicto is a volcanic island, and it did come to pass. This is a shot of the island. The volcano itself on the island is called Marcena, and so there's basically a shot of the island. The rock wren lived there along with various other critters, and as we can see, in August 1952, the volcano went boom. Catastrophe. Something that you can't predict and model because it happens on such an infrequent scale, but clearly an act of devastation. And what we find from this, so here's the island post-eruption, as you can see, pretty much completely denuded of life. If we look at some of the diagrams here, we can see, for example, this is showing distribution of land crabs on the island, and they really were shattered by the volcanic eruption, and it's taken them over 20 years to begin to recover. If we look across here we're looking at distribution of plants, and so we can look at this, and basically, so this is what it's like pre-eruption through to post-eruption, and then we can see the gradual colonisation of the island as a consequence of plant propagules drifting in on ocean currents, maybe being deposited in droppings of seabirds, and so on. But certainly, even by quite recent times, still not as vegetated as it was pre-eruption. And of course, a little rock wren, that particular subspecies existed on that island and nowhere else in the world. So a catastrophe, species taken out. Now, all the four factors of randomness and random chance increase in the magnitude of their effects as the population gets smaller. So the smaller the population, the more susceptible you are to all of those random causes. And it's important to remember that under the Corley paradigm, the declining population paradigm, small population is a consequence of decline. What pushed it? And as Corley himself expressed, populations don't just dwindle off to extinction, they get pushed. So something causing the initial decline, and then these random chance factors become vastly more important as the population shrinks. And it is sometimes referred to as the so-called extinction vortex. So what happens here is the population becomes smaller. That reduces genetic diversity. That's what heterozygosity is all about. Individuals lose genetic fitness. Fewer of them breed, fewer new individuals are recruited, and death rates go up. So the population declines further, and this vicious situation is known as an extinction vortex. So basically a reinforcing of all of these random problems as the population gets smaller, pushing it ever further downward. So intervention is necessary to remove the cause of the initial decline, and in some cases to attempt to mitigate the problems that are being caused within the extinction vortex. So looking ahead towards an examination that you guys will be undertaking cheerfully at the end of semester, I'm sure you're all looking forward to it, what kind of multiple choice questions might we ask about something such as we've covered today? Well, here's a question about metapopulations. Just take a moment to read it. You're being asked to find which of the four statements is least accurate. So you're looking for three statements that will be pretty much spot on, and a fourth that's maybe not quite right. Over to you guys. Which statement is least accurate?
B.
Okay, we have a vote for B, that all metapopulations are a result of fragmentation due to human impact. So the vote is for B. Anybody wish to contradict that? Yeah, you're sitting there thinking it's week one of the semester and he's asking us questions. What a dirty trick. It is in fact B. So of those statements there, yes, metapopulations occur in fragmented habitats. So-called sink subpopulations, and this is a really good point, I didn't mention this. We talk about sources and sinks for the subpopulations. In a sink subpopulation, you actually don't replace yourself. And so that one's correct. And so-called source subpopulations are ones where lots of new individuals are produced and they go on a wander and migrate to other patches. Metapopulations can occur naturally, they are not necessarily a result of human-caused habitat fragmentation. So, to wrap us all up, what you should be able to do after reviewing the lecture today is explain why we need to know about population biology as a key in conservation, define populations, explain what determines their size, define and explain both exponential and logistic growth, explain what metapopulations are, and finally make comments about various kinds of random events, stochasticity, that can influence the size of populations. That's us done for today. A reminder for you that the lecture slide notes are up on the website, so if you need to go and check those,